This will be page 3, I believe. So Newton's cooling law. Imagine something like this. Some of you know how to bake a cake. I don't, but I heard that you put dough in an oven. You set up at 350 degrees. If you wait long enough, then the cake will come out of it. The point is, when the cake comes out of it, it comes out of temperature of 350 degrees. Now you put it on top of the range to cool off, and eventually, if you wait long enough, it will cool off to room temperature. Let's say 75 degrees. Now, if you look at the temperature as a function of time, the temperature of the cake, it will be an exponential decay. Initially, the cake will cool rather quickly. The reason is there is a large difference between the initial temperature, the temperature that the cake was when it came out of the oven, 350 degrees, and the ambient temperature, the room temperature, 75 degrees. If you have a large change, then you drive a rapid rate of change. Later on, as the temperature cooling off and the temperature of the cake is close to 75 degrees, say 100 degrees, then the change is slowing down. Okay? So we are looking at a case where the cooling rate is proportional to the difference in temperature, delta T. So, the case where the cooling rate of a cooling object in this case the cake, is proportional to delta T, which is the temperature difference relative to the ambient temperature. By that I mean the temperature of the room. Okay, so we're going to say that in terms of nomenclature, let's say T of T, the temperature as a function of time, is the temperature of the cooling object. T sub 0 will be the initial temperature. In other words, that will be the 350 degrees coming off the oven. And another term will be T sub S. This will denote the ambient temperature, the temperature of the environment. In the example I gave you, this was the room temperature. Okay, because we said that the object is proportional to delta T, the temperature of the object, then, and the cooling rate, then we're going to say that d T prime of T is proportional to, not to T, but is proportional to delta T. Okay? And delta T will be the difference between T of T and the ambient temperature, like so. So instead of proportionality, we can say that T prime is equals to some constant times delta T, or we have the differential equation K equals to T prime over delta T. Compare it to what we learned before, y prime, K equals y prime over y. Okay? So, compared to k equals y prime over y. So to make t prime over delta t looks like y prime over y, we're going to define y of t, define a new function, define a function such as y of t, I'm sorry, will be t of t minus t of s or delta t. So my delta t will be substituted with y of t. So if you do this, now we have instead of, well, if you take the prime here, so strike that, okay? If you take the derivative, then y prime of t equals t prime of t minus t prime of s, but the ambient temperature is held as a constant, right? So this goes to 0, and we end up having y prime equals t prime. And now we're going to substitute, so we end up having k equals t prime over delta t. I can write it as y prime over y, and the solution, remember that this differential equation has only one solution, and the solution will be y sub 0 e to the power of k t, like so. And we're ready for an example at this point. Okay. So we got everything we need. So basically, the cooling law is a technique where we're going to substitute the temperature difference, delta T, or we're going to substitute the variable T with the variable Y, and we proceed as it is a decay function.